Hello and welcome. My name is Fabian Kurtz. I'm a researcher with the Communication Networks Institute at TU Dortmund University in Germany. Today I'd like to present you my talk titled Predictive 5G Uplink Slicing for Blockchain-Driven Smart Energy Contracts. The talk is structured as follows. First, a motivation for addressing energy grid challenges via blockchain-driven smart energy contracts is given. This is followed by a detailed look at how data-driven prediction of blockchain communication traffic is harnessed for this purpose. Next, the performance of the proposed 5G uplink slicing mechanism is evaluated. Finally, a conclusion and an outlook are given. As shown on the right, traditional energy grids typically have a unidirectional energy flow from large power plants down to the consumer level. Such large centralized power plants are increasingly displaced by renewable energy resources such as photovoltaics and wind power. This leads to a volatile feed-in of the renewable energies and also to a bidirectional energy flow, which is distributed throughout the power grid. This means there's a need for a decentralized regional balancing of energies and supplies and demand to stabilize the overall power grid. Recently, blockchain-based smart contracts have emerged to address these challenges. Nevertheless, they are associated with an increase in communication loads. This increase poses a challenge as energy grids rarely possess dedicated communication networks, particularly at the distribution grid level. Here, 5G network slicing promises to provide reliable communication on top of shared public network infrastructures. In this work, we thus propose a predictive scheduling mechanism for 5G uplink slicing, enabling efficient and reliable transmission of mission-critical smart contracts. As seen on the slide, the work is structured into three main parts. First, I'd like to start off by giving an overview of the scenario modeling and implementation concerning the Hyperledger Fabric blockchain network selected for this work. In an effort to derive realistic smart contract data traffic, we first create a detailed energy load and generation model based on real-world data. We first selected a district of a local town with 680 participants. Each of these participants is classified according to the type of building and energy consumption, i.e. commercial buildings, residential buildings, and so on. Each of these profiles is then coupled with a representative energy load profile, as shown here in the upper right corner. All of these models are then overlaid, resulting in a cumulative energy load profile shown on the lower right hand. The corresponding electrical feed-in comes from a local convention center which has deployed a photovoltaic system on its roof. The data is provided by a local utility and is shown as an overlay in the lower right-hand figure. This setup constitutes a local energy cell, i.e. a local grid section, with means of electricity generation as well as consumption. In the next step, this serves as a basis for the construction of smart contracts for balancing energy flows. To avoid an unnecessary transmission of electrical energy, generated power is consumed locally wherever possible. This is facilitated by smart contracts on an intracell level, with the resulting contracts per block interval given by the plot below. Excess energy is exported to neighboring cells within the power grid. This process is handled by extracell contracts. In case the photovoltaic system's feed-in is insufficient, energy is imported from outside the local area via extracell import smart contracts. Whenever fluctuating demand and generation require existing agreements to be changed, so-called dissolve contracts are used. The underlying control loop for generating these smart contracts is applied in 1-minute intervals. This results in the depicted data traffic burst and serves as input for the realization of a Hyperledger Fabric-based blockchain network. As shown on the right, a network with several orderers and peers was implemented. It connects to the photovoltaic system, as well as individual consumers within the chosen city district. All of these entities are embedded as virtual agents on a physical testing setup, shown in the lower left corner. Thus, a large-scale deployment is replicated within a lab environment, facilitating the process of measuring the resulting data flows to be transmitted across the 5G communication network. In the following section, I'll provide an overview of the deep learning-based mechanism for predicting uplink transmission generated by smart contracts within the selected energy grid area. As a first step, a long short-term memory network based on Keras and TensorFlow was created. For this, 60 samples of data traffic in 1-second intervals was used. The resulting model predicts data rate bursts as well as baseline loads caused by background processes of Hyperledger Fabric with an accuracy of 92 to 94%. Nevertheless, the lower right figures demonstrate a failure in fully capturing transaction duration. Hence, we enhanced the LSTM model's training process by including information about smart contract generation. Thereby, the duration of transaction is predicted more accurately. This reduces the mean absolute error, resulting in an improved model with about 99% accuracy. To improve the prediction and thus the assignment of 5G slice resources in the uplink, the model is applied to faster transmission intervals of 100 milliseconds as well. Here, the size of data transmission is predicted with reduced accuracy, while the timing is preserved. At a resolution of 10 to 1 millisecond, however, neither the forecasted timing nor the amount of data retains the same level of precision achieved before. The LSTM model is derived by aggregating these separate parts, thus incorporating both fast as well as slow processes within the Hyperledger Fabric network in charge of managing smart energy contracts. The observed mismatches between predicted and actual values of transmitted data sizes are highlighted by the figure on the left. This effect can be reduced by applying a fixed scaling factor determined by empirical means and will be referred to as over-provisioning for the remainder of this talk. On the right, another figure gives a first indication of the increase in efficiency achievable through the introduced model. Compared to a fixed allocation of communication resources, this aggregated data-driven prediction model significantly reduces the mean absolute error in terms of wasted 5G uplink resources. For a baseline comparison, we also include this analytic model. Here we performed an analysis of smart contract transmission measured within the testing setup. Results are plotted in the figure on the left, including block and transaction volumes as well as their duration. As can be seen, these metrics mostly show linear behavior, enabling a straightforward analytic modeling. On the right, the data rate over time is given for an order within the Hyperledger Fabric network. Here we approximate actual traffic via a rectangular step function. Bursts in data rate are, however, difficult to capture due to their highly variable occurrence. In the final section of this talk, I will now focus on the implemented network slicing simulation and overall evaluation results. Slicing, i.e. the separation of a single physical network into multiple virtually dedicated communication infrastructures, is a key feature of 5G. Nevertheless, several approaches for realizing this vision exist. The most straightforward approach, i.e. static slicing, as shown on the top, assigns a fixed set of air interface resources per slice. Thus, so-called resource blocks, as shown by the figure, may oftentimes be assigned without actually being required. These resources cannot be used by transmissions in other slices and are thus wasted. Lastly, data rates exceeding slice capacity lead to loss of data packets. These shortcomings are addressed by dynamic reactive slicing, in which slices are not configured with fixed maximum data rates, but with peak, average, and minimum guarantees. Hence, fluctuating requirements in terms of capacity can be met more easily by reducing inefficiencies and package loss. In this work, we propose to extend this approach via the inclusion of deep learning for dynamic predictive 5G uplink slicing. For this, we built on 5G's configured grant mechanism as implemented within a self-developed simulation framework introduced in previous work. Before transmitting any data, devices traditionally need to request access to the air interface. This is then granted by the corresponding 5G base station. Configured grants, however, are a mechanism for enabling base stations to allocate resource blocks without devices having to request them. Thus, the scheduling request can be avoided, reducing end-to-end latencies. Any failure in forecasting resource usage may result in package loss and increased latencies. Hence, this approach requires a precise prediction of transmissions as facilitated by the proposed LSTM model. The evaluation scenario at hand considers three slices: the smart contract slice, the grid control slice, and the best effort slice, all assigned with different requirements in terms of data rate, latency, as well as priority. In static slicing, the average latency caused by scheduling increases with decreased priority per slice. The dynamic reactive slicing approach achieves a latency of 1 millisecond for all slices and increases spectral efficiency. The dynamic predictive approach, based on an analytic model, increases the latency of the smart contract slice by 21%, but decreases latency for both other slices nearly down to 0 millisecond, as scheduling can be avoided. The dynamic predictive slicing based on machine learning shows similar results, although increasing latency of the smart contract slice by only 5%, thus being preferable to the analytic model. Significant reduction in latencies for all slices can be observed when coupling the machine learning-based approach with over-provisioning as based on empirical values. Here we can show a reduction of latencies of around minus 61% and thus achieving significant gains. Next, we're going to have a look at how this impacts the actual utilization of 5G air interface resources. The plot depicts which share of all available physical resources are assigned to which slice. As can be seen for static slicing, a large proportion of the slice is actually unused during most of the time. In this case, this is more than 60% of all air interface resources. Applying the dynamic predictive model, we can see that 45% of resources are actually freed up at the cost of a small increase in latency, as discussed on the previous slide. Furthermore, it can be seen that the amount of used resources increases as no traffic is actually being lost due to static assignment of slice resources. Finally, when coupling the dynamic predictive approach driven by machine learning with over-provisioning, we can see that the latency is further reduced at a cost of 20% additional total allocated resources. This constitutes an increase to 37% of free air interface resources in the uplink and a latency reduction of 61% compared to static slicing. This clearly demonstrates the effectiveness of the proposed solution approach to assigning 5G uplink resources in blockchain-driven smart energy contracts. In conclusion, this work created a realistic energy model for balancing power flows on a local level. It was used as input to drive the implementation of the Hyperledger Fabric-based smart energy contract framework on a physical testbed, thus resulting in real smart contract transmission which were recorded and used for the development of a deep learning-based communication traffic prediction model. The evaluation of the proposed 5G uplink slicing achieved a demonstration of up to 61% lower latencies while using 37% less resources. Future work will strive to achieve validation within a physical 5G network within a smart grid lab environment, as shown on the right-hand side. Further optimization of the deep learning-driven 5G uplink slicing approach will also be performed to enhance the presented approach. This concludes my talk. If you would like to know more about this topic or receive information about the Communication Networks Institute's further activities, please feel free to get in touch with us via the supplied contact information and websites. Thank you for your attention.